Quality of Service Part 3, Policing, Shaping, and Link Efficiency. Well, as we round out the quality of service nuggets, we are now going to take a look at one of the most critical topics, I believe, to networks today, and that is going to be network policing. Now, shaping comes in, and a lot of you have seen shaping if you went through the early wide area network configuration nuggets, and we talked about frame relay traffic shaping. This is going to be that same topic, except how you can implement it in the quality of service setting of the modular QoS CLI. Policing, on the other hand, is awesome. And that's because you get to limit traffic, just like this guy standing right here. You get to say when to go and when to stop. We're going to get into what it's all about and all the terms you'll need to know, and then we'll get into the actual configuration of policing and shaping as we go into here. Then we'll take a look at an in-depth study of link fragmentation and interleaving, also known as a link efficiency mechanism. And also falling under that same category of link efficiency is compression. We're going to really round this all out by showing you how to make your links that much more efficient. I have a friend who works out at one of the major universities out here in Arizona. I won't tell you which major university to protect the innocent. However, he had a really interesting situation it's been about a year ago now. That was when P2P applications, peer-to-peer applications, were really starting to take off, and a lot of people were starting to use them. And the problem is that his university internet connection could not handle hundreds of students in the dorm rooms, leaving these programs open all the time, sending and receiving music and who knows what else from these file sharing applications. So his initial reaction was, you know what, I'm going to cut it off. And he denied the access to those applications at the router. Now, to make a long story short, let me say that did you know that P2P applications, peer-to-peer applications, could be considered freedom of speech? Well, they can be, and sure enough, within a few days, he had to start allowing access to those applications yet again. However, there is a way that you can make it much more efficient while still allowing access to keep those applications from gobbling up all your bandwidth. That is where policing comes in. Now, when you first look at these graphs and you go policing, shaping, you look at shaping, you go, wow, that just looks a lot better with bandwidth utilization. And the truth is shaping really is. Policing is meant to cut traffic off as soon as it reaches a certain traffic rate. Now, the nice thing about policing is that you can apply this feature incoming or outgoing on any interface of your router. That's not true for a lot of the other quality of service mechanisms. You can only go outgoing for most of them. So this can actually cut things off as they're coming in. The excess traffic will either be dropped completely, and that's most often what happened, or remarked to where you can say, well, it came in with IP precedence of 5, but I want to knock it down to IP precedence of 2 since we've exceeded our traffic limit. This obviously uses less memory buffers than some of the other mechanisms because it doesn't buffer anything. It just cuts it off as soon as it reaches a certain limit. Not so with traffic shaping. This is something that I think most of us are familiar with. On traffic shaping, it can be applied outgoing only as things are leaving your router, and any of the excess traffic that is exceeding your set rate will be queued in memory buffers. So it's going to store it up and try and send it at a later time. Now, obviously, if you reach a certain limit, it will end up having to drop some traffic when your queues fill up. This is something that is typically used in frame relay and ATM networks to shape traffics because you could have speed mismatches on the side. Only in those NBMA style networks can you have a T1 line matched up to a 64K committed information rate on the other side. So you're going to have to shape that so one side does not overwhelm the other. So before you can start implementing policing and shaping on your Cisco router, you need to understand the terminology that's going to be used. I mean, these are going to be things that you have to fill in the context-sensitive help. You'll need to set levels of traffic. And those levels can be one of three things: conforming traffic, exceeding traffic, and the forbidden violating traffic. Now, with these different traffic levels, you get to set speeds for these. So let's say, I'll stick with the same thing. Let's say we're trying to limit peer-to-peer applications, P2P. Now, for that traffic class, I want to set a conforming level of, we'll say, 100 kilobits per second, an exceeding level of 200 kilobits per second, and then I'll talk about the violating in just a second. So let's say we stick this on our network and we get some traffic coming in. You see somebody open their Kazaa or whatever application that may be, and they're kind of floating around here in the conforming of 50 kilobits per second, and then someone else opens theirs, and so you're right above the level in the exceeding territory and kind of float around there, and someone opened theirs, and now you're into the violating area, and your traffic is sitting up here. Now you, as the administrator, get to define exactly what is going to happen at each one of those three levels. So let's say for conforming, you say, you know what, I'm ready to handle that kind of impact to my network. I'm going to transmit traffic that conforms to that standard. If it exceeds, just for the sake of this argument, we'll say if it exceeds my level, I want to go ahead and I want to set the IP precedence to 0, but still transmit it. So that way, maybe at a router further down the line, if it is experiencing congestion, it will go ahead and drop things with IP precedence 0 using maybe weighted random relay detection or some other mechanism. Now, if it violates this set level of 200 kilobits per second, anything above that, I want to say I want to drop that traffic. So what you have here is 3 levels of control that you can use. Now, do you have to use all 3? I mean, this one's kind of a stretch right here. You could tell I kind of struggled there because, I mean, do we really want to set the IP precedence of Kazaa or peer-to-peer applications to 0? Probably not, because that's probably what it's going to be anyway. All traffic that's at that level will have the IP precedence of 0. The reason I have this here is because I want to show you the flexibility. You don't have to define a violating area. You could say, as soon as that P2P application exceeds that, or that traffic class, let's get specific, that traffic class exceeds it, I might want to say I want to drop it right here, as soon as it goes above 100 kilobits per second. These are defined, these levels are defined for each class of traffic that you set up. Now remember, let's say the term class map can include whatever traffic you want. You could say I want the P2P applications. You could say I just want one of those applications. Maybe I just want SQL or web traffic. Whatever you define in that class is what you can shape or police for. And we're going to get, when we get into the configuration, you'll be seeing each one of those terms. So let's do that right now. So I'm going to bring up a connection to one of my routers here, and let's go ahead and start doing policing and use these terms in our configuration and show you how they apply on the real equipment. Now this is a live router. It does have real traffic going through it. So I'm going to go in here and create a class map. And I'm going to create a class map for Kazaa. Because this is actually a head-end router at one of the places that I manage on a regular basis, and I did some monitoring beforehand, and I saw that there's plenty of people using Kazaa right now, so I want to be able to limit those people. I'm going to create a class map of Kazaa, and I'll do a match protocol of, and we should see it right here in the list, there it is, Kazaa. Kazaa version 2 is what everybody's using nowadays. So I'm matching that specific protocol. Now I could match more of the P2P applications, but for now I'll just keep it to a single protocol. From here, using our MQC standard, what's next? The policy map. So I'm going to type in policy map followed by the name. I'll name it just lim for limit. And I'm going to say for the class Kazaa, the class map that I just defined a moment ago that matched the Kazaa version 2 traffic, I want to, and I'll hit question mark, and there's my options. I'm sure you can instantly glance and see, aha, police or shape. Those are the two topics we're talking about right now. Well, when I'm talking Kazaa, I don't want to waste my memory buffers on queuing that traffic with shaping. I want to police that stuff. So I'm going to type in police followed by, and then I can type my levels. I want to say, for my, now the terms are blurring in my mind, for the conforming traffic, that's what I see right here, I want to limit it to, let's say, 10 kilobits per second or 10,000 bits per second, which looks like a lot, but really is somewhere around less than half of a 28.8 modem. I'm going to hit enter at that point, and now I'm in the policy class police mode. We get deeper and deeper. I'm going to say, okay, from here, if it's conforming to my 10 kilobits per second, then I want to transmit it. You see it in the last one, and you can see from this list I have the option of drop. I can set certain bits. I can say, well, I'm going to set maybe the DSCP layer 3 bit. I can set the IP precedence, frame relay discard eligible, MPLS bits. I have a whole bunch of options, but we'll keep it simple for this. I just want to transmit that traffic that is conforming to the 10 kilobits per second. For the exceed action, when something is exceeding, I want to, you know, I don't even want to use all three of these because I don't want any in between. I want to drop it if it starts exceeding that. And I'm not even going to define a violating level, because if it goes above the conform and hits the exceed, then I'm going to drop it. But let's say you wanted to. You might be thinking, well, I thought you just typed in 10,000. How would you define the different levels if you needed to do more, like the exceeding level? Well, when I did this, I typed in police followed by 10,000 bits per second, and then I hit enter. But if I wanted to start defining an exceed level, I could type in a second value. It's synonymous with a burst byte. So I could say when it exceeds this number of bytes, I'm in the exceed range. Violate, I don't type anything in, because violate is considered once you've gone past conforming, once you've gone past exceeding, anything that is above that is considered violating. So that's how we would configure it. From there, my last thing is going to be to apply it. Let me just do a show IP nbar protocol discovery, and I'm going to do the stats bitrate top 10. It's a long command. I actually have an alias set up for it, but I figure I show you the whole command so that you can see what traffic is currently being used on this network. Now, as of right now, I've got quite a number of individuals using HTTP, and it looks like some people are using Kazaa version 2. Looks like we've got some traffic. I don't know if it'll be enough to push the limits, but let's go ahead and apply that policy. I'm going to go into the interface serial 0, which is the internet connection, the T1 line out, and I'm going to type in service policy, and I named it lim, right? But I need to determine whether it's inbound or outbound. Well, looking at these traffic patterns, and especially when you're talking P2P applications, it could be a lot of inbound and a lot of outbound. We have, in this case, more inputs than output. Somebody is sending using Kazaa rather than receiving a lot of traffic. So what I usually do when I start limiting these applications, since policing, the major benefit was that it can be applied inbound and outbound, I usually apply it in both directions. That way, I limit it both ways. Otherwise, they may get around my policy if they just upload a lot, or maybe download a lot if I applied it on the input. So I'm going to say inbound. I'll do input first, and I'll say the policy map name is lim. From there, I'm going to type in service policy output, lim. When I jump back out here, I can do it does it over 5 minutes, so we might need to pause the recording, but let's see if it's caught any traffic already. I have an alias called traffic that does that same exact command that I typed before, and we can already see it's starting to affect it over a 5-minute range. It's gone down, and this is on the serial interface, and down here I have it monitoring the fast Ethernet connecting to the LAN. So if I just keep doing this traffic and start watching it, you can see, well, because I went back up a little bit, but overall it's going to stay below 10 kilobits per second. I'll show you a more specific monitoring command. I'll do show policy map interface S0. And what I see here is service policy lim, and what I've got, look at this great data, guys. Committed information rate of 10 kilobits per second. I have 83 packets that conform to that, so about 30,000 bytes, 30 kilobytes made it through. 55 packets exceeded that, so about 50 kilobytes have ended up being dropped. Now that's since I've actually applied this policy, only 138 packets. As you watch it over time, you're going to start seeing the true long-term effects of applying that policing policy to this router. So policing is an awesome and much needed way that we can control the traffic that's going through our network and make sure that it doesn't exceed certain amounts. Let me go ahead and turn to shaping and the shaping side of things. And I don't want to spend too much time here. If you really want the foundation of what shaping is all about, then definitely check out the wide area network configuration nugget that's focused on frame relay traffic shaping. This is the same thing as frame relay traffic shaping, except it's applied using the MQC standard. standard. And you can expect over time Cisco is going to be moving all of those kind of odd configurations that you would apply from the map class mode instead of class map, and they're probably going to be moving all of that to the new standard of MQC pretty soon and discontinuing the old way so that they can all focus around the same way of doing it. They've also made it much easier to use MQC than it was when you were using the old frame relay method of doing it. What we need to do is go in here, and I'll create a class map again, and I'll name this one web. I'm going to say match protocol HTTP. Get out of that class map configuration mode. My router's thinking about that. And I'm going to do a policy map, and we'll do shape will be the name of this policy map. From here, I'm going to type in class web. That's the class I just typed before. And now I can choose shape instead of police that I have here above. I'm going to type in shape. And from here, you can see these are starting to become frame relay terms to where you can have it be feck adapt or beckon adaptive and respond in shape to beckons. You can see they've taken a lot of the same shaping configuration from the map class configuration mode, which was how we apply frame relay traffic shaping in what I call the legacy days, which wasn't all that long ago. Now we can go ahead and shape it this way. And the nice thing about it is they've made it much easier. To implement standard traffic shaping, you just need to type in either shape average or shape peak, one of these two terms. If I type in shape average, followed by what I want my CIR to be or what percentage of the bandwidth configured on the interface I want to use, if I type in shape average, it's going to shape it around the CIR. So I can say, well, I want to shape average, and we'll say 100 kilobits per second, which is 100,000 bits per second. At that point, I'm done. You can get specific and start getting into the committed burst, B sub C, and again, that comes from the frame relay traffic shaping chapter, and you can even get into the B sub E for the excess burst, but really, Cisco says you shouldn't use it. The reason why is Cisco will figure out, this router will figure out those values for you. Now, if you type in shape average, it's going to shape it at the CIR, what your CIR is going to be. If you type in shape peak, it will shape, instead of the CIR, it will shape around the excess burst. It will actually go up above, and that's considered the PIR when you get into the peak information rate instead of the committed information rate. And this all depends on how risky you're feeling. You know, if you want to make sure all your traffic gets there, do a shape average. Make sure that you always stay at or below the CIR. By doing a shape peak, you can guarantee that some of your traffic is going to be tagged as discard eligible. Now, will it be dropped? Well, that's up to the service provider and what their congestion is at that time. So you're going to need to work with them and really figure out what their policies are on their traffic to determine whether you use shape average or shape peak. But the nice thing is, with MQC, that's all you need to do. Cisco actually says, if you look at their documentations, don't type in a B sub C or a B sub E right here unless you absolutely must, or you know what you're doing, because the Cisco router will figure out for you. Once you're done with that, all you need to do is apply that shaping policy to the interface using the service policy output command. Remember, policing can be applied inbound or outbound, or I should say. Shaping can only be applied in the outbound direction. Well, let's take our turn into the link efficiency mechanisms. And I'm sure right now you're looking at the screen going, right, what is that all about? Well, this goes into the story of what link fragmentation and interleaving is all about. Imagine that you got the coolest sports car in the world and painted in backwards #1 on the side for whatever reason. And you are so excited about the sports car, you just want to drive that sport car as fast as you can everywhere. So that's you sitting in that sport car, sitting behind this huge truck, and you're sitting at this light and you're kind of anxious, waiting for that light to change, and the light suddenly does turn green. This truck kind of starts, shifting into first, and it's going really slow. Let me see if I can make this truck move here. It's going, really slow, going through the intersection, and by the time it's said and done, oh, it made it through, but what happened? It got by, but the light is now red. So you go up here with your sport car, and now you're staring at the red light. Oh, you're going to have to wait until you hit the freeway to test out the capabilities of that sport car. So how could we have fixed that situation? The quickest way would probably be to blow up the truck, to go ahead and chop the truck into mini pieces. And okay, it's an analogy, follow it here. With that truck chopped into mini pieces, you strapped explosives and blew it into little chunks. Your little sport car can kind of go zip, zip, and zip around and weave its way into and through, oh, I lost control of my sports car, weave its way into and through that truck and make it through the intersection off into the freeway at light speed before it could ever get that light change red again and you get stuck at the light. That is kind of a parallel to what link fragmentation and interleaving is all about. But instead of sports cars and Mack trucks going through lights, we have data frames and voice frames. Now your data frames, and I kept the stoplight on here because it paints a good picture. The data frame is 1,500 bytes. 1,500 bytes. It's the Mack truck of your network. The voice frames, if you're using G.729 codecs and compression and things like that, are probably going to be somewhere around 30 bytes each. They're the tiny little sports cars of the network. Now here's the problem. Imagine that you have a 56K modem connection. I'll put 56 kilobit per second. For the 56 kilobit per second to transmit a 1,500 byte frame, it takes about 214 milliseconds to allow that frame to go through. Now looking at that in our terms, you're thinking, well, that's not bad. 200 or so milliseconds, that's not even a second. Well, that is until you realize that for voice to be of good quality, it must get from one end to the other in 150 milliseconds or less. Ugh. So at this point, we've already exceeded our delay budget for voice. It's going to be poor quality before it even leaves the interface because it's been delayed by that data frame. What we are able to do is literally chop that data frame up into little bits, just like we did with our Mack truck. By slicing it, oh, let me change colors here. By chopping this into little bits and making it smaller, we can then do what's called interleaving on our voice frames and squeeze them in between the pieces of those data frames and then send it out the interfaces. That's known as link fragmentation, chopping it up, and interleaving, that's the I, that splices the voice frames in. Now there's two ways that you can configure LFI on a Cisco router. Now, I shouldn't say there's only two ways. There's actually many ways when you get to frame relay native networks and not using IP and things like that. But for the real world, these are the two most popular methods that you'll always see. Multi-link PPP is used on point-to-point connections, serial links typically, and FRF12 is used for voice over IP over frame relay networks. That means you're running the TCP/IP protocol and you're running it across frame relay, which 99% of the world is really doing. Just so you know, you might see this one as well, FRF.11 Annex C. That's actually LFI for frame relay, not voice over IP over frame relay. It's just voice over frame relay where there's no IP involved, which is a very rare occurrence. Now trust me, I can already feel the wheels turning in your head because they turned in my head when somebody showed me this and they said, oh yeah, multi-link PPP can be used to do LFI on a serial interface. And I thought, well, yeah, the multi-link PPP, that's great if you were bundling multiple links together. I mean, I've always seen multi-link PPP used to like bundle multiple B channels on an ISDN line. But the note about it is that you can do multi-link PPP on a single interface. Now, before I show you that configuration, let me tell you why. Multi-link PPP has a feature that allows it to load balance between multiple interfaces exactly. I mean, dead on, byte for byte. If you have multiple B channels in an ISDN interface, you want it to send equal data amounts across those when you bundle them together. So what multi-link PPP does as the packet's getting ready to leave the interface is it literally chops that packet up into exactly equal pieces and sends it across the 2 different B channels, or however many B channels you have. I think this is kind of already pointing in the direction that we're going to be going with this. Let me show you the configuration of how you do this on a single serial interface, and then I'll show you the kind of fill in the why behind it. The first thing I'm going to do is get in here, and I'm going to create a new type of interface that you might not have seen before. It is a multi-link interface. I'll do interface multi-link followed by a group number, and you can choose any number that you want. I'll go ahead and use 1. This is a virtual interface that you're going to use for your serial interface that you're going to add in here and allow it to do LFI over this interface. So I could, type in an IP address 10.1.1.1, but I really want to stick it to the commands that you're going to need to just do LFI, because this is going to be where you put all the logical configuration of that interface. So I'm going to type in PPP multi-link. Now I'm going to type in PPP multi-link followed by fragment, because you get to specify your fragmentation parameters, and then I get to specify the delay. Look at this. What I can do, and this is a powerful command, is specify how much delay I want a packet to have when it leaves the interface. Now I mentioned up here that a data packet, 1500 bytes on a 56K modem, has 214 milliseconds of delay. Well, Cisco's recommendation for voice is that you have no more than 10 milliseconds of delay for voice packets. So I'm going to hit fragment delay 10, and that will make sure, and it will chop it up into pieces that are small enough that it will only take 10 milliseconds to send. The reason I say it's so powerful is because, wow, it does all the math for us. We don't need to tell it what size of packets we want. We just tell it what delay we want to meet, and it will take care of the math behind how big of the packets need to be. Now I'm also going to type in PPP multi-link interleave, because it's one thing to chop that packet up into small delay segments, but it's quite another to start splicing the higher priority packets in between that. That's what the interleave command does. Now from there you need to specify how much bandwidth you have on that interface so that it can accurately figure out how small of a chunks the packets need to be split up into. I'm going to say 500 kilobits per second is the bandwidth on that multi-link interface. And for now, that'll be all the configuration I need to type in. That does the fragmentation. To apply this to a single serial interface, I'll type in interface serial 0/0, and I'll just type in encapsulation PPP followed by the command multi-link, or actually, sorry, PPP multi-link group 1. The reason I was typing it up here is just multi-link. Some iOS versions actually have that as its own command. You just type in multi-link dash group 1. Newer iOS versions have it tied to PPP multi-link. So I type in PPP multi-link group 1, and what does that do? Links that serial interface, a single serial interface, right up to interface multi-link 1. It ties those 2 logical configurations together, and now we have implemented PPP multi-link on a single serial interface. The last thing I want to talk about is compression. How you can make your link more efficient. It falls right under that link efficiency mechanism category. Now there's 2 types of compression. I'm only going to talk about one. Payload compression is kind of the default compression when everybody thinks about compression that you can apply to an interface. We talked about that in the PPP WAN configuration nugget, where you can just go under that interface and type in compress, and you can either choose the predictor or stacker or the MPPC for Microsoft point-to-point clients compression mechanisms, and it compresses the link as a whole. That is not what I want to talk about here. That's more of a link, a wide area network configuration. I want to talk about header compression, because header compression, as it starts getting into quality of service, which primarily deals with voice and video traffic, plays a really big role in our networks. First off, there are 2 types of header compressions. We can use RTP header compression and TCP header compression. The main one that I've used in most environments is RTP. RTP stands for the real-time protocol. It is the protocol that transports H.323 audio streams or voice over IP traffic across networks. Now here's the wild thing. On average, most headers, including the IP header, the UDP header, all of the layer 2 header information, those headers total about 40 bytes. Now, when you start thinking about a voice packet that on average has about 8 bytes of data, if you're using a compressed audio, which most people are, you're really looking at a horrible ratio there of data to actual packet size, because you figure 8 bytes is the voice, 40 bytes is just the header. I mean, that's a horrible ratio. Well, with RTP header compression, you can actually reduce that 40 bytes down to 2 to 4 bytes of data. Holy cow! 2 to 4 bytes? WinZip better get a hold of these people, because they figured out some kind of compression algorithm that's phenomenal. Well, the truth be told, it's not truly a compression algorithm. The name is a little bit of a misnomer. Here's the idea of how RTP and even TCP header compression works. If you look at a packet and you were to kind of break open the header and look inside, what would you see? Well, you'd probably see things like the source IP address, the destination IP address, maybe the source MAC address, the destination MAC address, port numbers that are going through, all of that kind of, well, frankly, repetitive information. Let's say it this way. Let's say that you're talking from one device to another and you're going to send 1,000 packets between them. What are the chances of the source and destination MAC address changing? Well, unless you replace a network card in the middle of that conversation, probably pretty slim. How about the source and destination IP address? Well, pretty slim as well. So what RTP header compression does is simply remove that information from the header. It caches the information. The first packet will have a full 40-byte header, but every packet that follows going to the same destination is essentially gutted. It takes all of the IP address and MAC address and all that repetitive information out of the packet and reduces the size of the packet to a very, very small amount. Now, obviously, that should let you know that if you are planning on using RTP or TCP header compression, TCP is just for the TCP side of things. The reason I don't talk about it much is because most of the time, if you're doing this kind of compression, you'll jump back up and just use a full payload compression. RTP is mainly the one people use for just voice. But both of these have to be enabled on both sides of the link. If you send a packet that's missing a ton of information to the other side and it doesn't have it enabled, the router's going to say, hey, this packet's corrupted. It's missing all of the information that it has, and it will drop it. So it's definitely critical you turn it on both sides. Now, payload compression is enabled under interface configuration mode, and again, I'll refer you back to the wide area network configuration nuggets for that. Header compression, on the other hand, is configured from our friend, the MQC. This is how easy it is. I'll define a class map and I'll call it voice. I'll match the protocol of RTP, which matches the streaming audio packets. I'll then do a policy map, name it voice, and I'll match the class voice. And then I'll type in compress, followed by what type of header compression I want. I can type in compress header IP RTP. That's RTP header compression. If I want to enable TCP header compression, I can do that as well, but since RTP runs on top of the UDP protocol, TCP header compression isn't going to affect it in the slightest. That's it. That's all you need to do from that policy configuration mode. Now, the thing is this is usually combined with many other policies. I enabled compression, but I would also start saying from here, maybe enable low latency queuing and do a priority followed by a certain, percentage of the interface bandwidth that I want to dedicate to voice traffic. So I now compress the headers and reserve priority bandwidth for that voice. But that's all there really is to enable that RTP header compression, and then you just apply it to the interface. In this nugget, we have taken a look at a lot of ways that we can use quality of service measures to optimize our links. First off, starting off with the policing and shaping mechanisms, which I'm sure gave you many ideas of ways that you can now make your own network in your corporate environment more efficient by implementing policing for those less priority traffic. And here's a tip, by the way. Most people, if you police the P2P applications, most people will never notice. The reason why is peer-to-peer applications rely on not only your bandwidth, but whoever's bandwidth you're connecting to as well. So if it starts going a lot slower, people will most likely just assume, well, hey, whoever I'm connecting to has a slow internet connection. So I have enabled policing in many environments, and nobody has ever known a thing other than the people that use the network for real things. They're thinking, wow, the network suddenly got faster when accessing the internet. Now from there we went through link fragmentation and interleaving in all its glory. We looked at multi-link PPP configuration and how to set that up on the interface, and then we topped it off with class-based compression, using class-based compression in the MQC to compress either the RTP or TCP header of the packet that's going through your router. I hope this nugget has been informative for you, and I'd like to thank you for viewing.